Okay, so this was a talk I gave in 2017. Did not have JavaScript in mind at all, although I was on the committee at the time, but this was part of a separate project I was involved in, which was a data log-like language that I was working on at Google. A language derived from, called Yetalog, a language derived from that eventually did get released by Google open source called Logic A, but Logic A has enough differences that I don't claim any of what I'm about to present has any relationship to Logic A, and since this is a JavaScript audience, I am going to say as little as possible about logic programming, horn clauses, data log, just enough to set up, to make the points, to explain the points in the talk that are relevant to JavaScript, relevant takeaways to JavaScript. So really this is about uncanny valleys in language design in general. Okay, so the term, this is a diagram from the famous Uncanny Valley paper. The Uncanny Valley paper was about rendering, people trying to do computer graphics movies with human characters in them. And what the paper shows is that down here at the left end is like cartoon characters, the kind of characters that might appear in Bugs Bunny. And then, as you get increasingly human-like, looking at a toy robot or something, as you get increasingly towards human-like, generally people like it. Oh, I'm sorry. Okay, now you can see my cursor. People tend to like it better until you hit this uncanny valley, where you're close enough to human, but still not quite close enough. There's this weird uncanny valley between things that are sort of obviously not human and things that are really impressively, plausibly human, actual human. Between the two, there's this uncanny valley where people get a creepy feeling. People are repelled by it. They don't like it. Now, in language design, I don't care about creepiness, but the uncanny valley that this talk is concerned about is very, very much like this, and I would say, generalizing a bit, for the same reason. And the way to think of the reason is that there's the actual likeness to what you're trying to present, the actual fidelity, and then there's, once you're looking at something of that fidelity, what do you expect? And then how does the actual differ from your expectation? So as you rise up towards the uncanny valley, the actual and expectation are aligned. Then, once you enter the uncanny valley, essentially things look realistic enough that it leads your mind to form an expectation that things will really be realistic. So they're close enough to provoke you to form that expectation, perceptual expectation, and then it disappoints the expectation. But then, as the actual continues to improve, it comes back out of the valley, it meets the expectation, and everything is wonderful. Okay. So normally I explained back then I explained the Java column. Today I'm going to explain the ECMAScript 3 column. But all of these are uncanny valleys in language design. And the case in ECMAScript 3 was that ECMAScript 3 only had sloppy mode. Strict mode had not yet been invented. And if you assign to a property of an object, and that property is read-only, the assignment will fail silently. The language, so that's the language as designed. The language as implemented is that there were very, very few properties that were read-only, and in fact, the programmer was not empowered to create such properties. It was only the host that could create such properties. And because there were very few of these, people rarely encountered these silent failures, so they would write their code assuming, so here's a general theme of this whole thing, which is people do not learn the semantics of a language primarily by reading a manual or listening to any formal explanation or anything. They primarily learn the language by trying things out and seeing what happens, and then from their experience, they form an intuitive theory. They generalize from their experience to an intuitive theory, which might be very different than what the language designer had in mind when they designed it. So the intuitive theory in ECMAScript 3 was basically assignments succeed, and it was supported by almost all use. And then this discrepancy between what the language was specified as doing and the language as it was assumed, we then adapted to the discrepancy between these three rows by inventing strict mode. And this is often a dynamic in language evolution. These three rows diverge somehow. There's a discrepancy. That discrepancy leads to unpleasant anomalies. And then rather than beat programmers over the head saying, no, 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 you shouldn't have assumed that assignments would succeed if they were silent. Instead of doing that, you can learn from what programmers understood and see if you can grow the language towards their expectations so that now the expectations that they formed anyway turn out to be correct. You've sort of grandfathered in intuitive programs into being correct programs. So you can think of this language design landscape as expressiveness versus automation. I'm sorry, let me back up again. So in the upper right corner is the perfect language, which is unachievable, where you just say what you want, and you leave it up to the language implementation to figure out how to give you what you want, and there's no limit into what you can say you want, and the language will always provide it well. So let's assume that's unachievable, but it's the attempt to get there from multiple angles that creates much of the variety of programming languages we have in the world. So this cloud in the upper left, which includes JavaScript, is sort of the conventional imperative imperative language with synchronous mutable state. And those are incredibly expressive. You can solve all sorts of problems, but they are very non-automated. They make you figure out how to solve the problem. The algorithm comes from you. The algorithm does not come from the language implementation. The other extreme, data log and SQL, are declarative languages whose expressiveness is purposely limited in order to only be able to ask it to do decidable things. The only questions you can phrase, the only things you can ask it to, you can express, are decidable questions. And then you completely leave it up to all sorts of fancy optimization engines which can change over time and which are just this big black box that almost all programmers are just unaware of, because somehow it just magically figures out a reasonably good algorithm to produce the answer, and even when it's not reasonably good, because it's all decidable, it'll always give you an answer. Okay, so because we're not talking specifically about declarative languages here, I'll skip some of this. Just that we start with the expressive languages, and we might try to make them more automated over time, taking us into this middle territory. We might start with the declarative languages, and try to make them more expressive over time. So both of those are kind of entering into this area in the middle, and the coloring here is there we go. The coloring here is to indicate that the sweet spots, the hills that you want to climb, where the discoveries of new languages that make a different trade-off between expressiveness and automation, might be guarded by an uncanny valley that you have to get through to get there. So, this is a horn clause. It has a declarative logical reading in terms of implication, conjunction, disjunction. And that's not what's interesting for this talk. What's interesting for the talk is the contrast between prologue and datalog, which is and yetalog, which is in prologue. There's no automation in the sense that it's not magically inventing an algorithm that's not what you wrote down. It's completely 100% the programmer's responsibility to guide the order of computation, and it's this, guaranteed left to right, top to bottom order that gives the programmer complete control of the control flow. And if the programmer writes something that never terminates, well, that's on them. It's very easy to write something that never terminates. Datalog leaves the ordering implementations to the decisions, tremendous sophisticated query optimization, but there's a limit on what questions you can ask. Yetalog starts with datalog, tries to make it more expressive, but once it's more expressive, it's easy for the built-in optimizations to lead you off a cliff of non-termination or something, because it's no longer decidable. So we introduce explicit control operators for taking control back from the optimizer and say, okay, I'm insisting that it goes left to right here. Okay, so so this is enough to explain sort of the heart of the talk, which is I did a survey internal at Google asking people, write recursive factorial in yetalog. These were experienced yetalog programmers. And almost all of them wrote factorial in this way. You can think of this as on a spectrum of 4 different ways to write factorial. All of these, in terms of the declarative reading, are all mathematically correct. All of them, in terms of the conjunction, disjunction, all of the mathematical reading of the horn clause, independent of control, all succeed at express factorial. But in yetalog, this one will guarantee never to terminate because it just counts up forever. This one just counts down forever. But what people wrote was essentially the one that counts down, the top-down recursive factorial, but guarding it with this n greater than or equal to 1. And because they did not say and, we were actually in the territory where we're leaving it up to the language implementation to choose some order. We're not taking control away from the language. So that happened to work in the implementation we provided, because it was just sort of a consequence by accident, if you will, of the optimizations that we did do. So it would always work in the actual implementation, but by the language semantics we tried to teach, this was an incorrect program. The correct program is factorial D, which I can say, I think I remember this correctly. It's in the paper and the talk. But I think nobody in the survey wrote factorial D. So this sets us up for this slide as it develops is really the punchline of the talk, which is a programming language can be seen from 3 different perspectives. There's the language as designed, in the language as we designed Yetilog, factorial A and B must not work. It's guaranteed in the Yetilog semantics that it won't work. Factorial D is actually the correct program that by the semantics must work. What everybody wrote is factorial C, which by the semantics of the language, by the language as designed, may or may not work. It's allowed to work, but it's also allowed not to work, both of which can be a property of a correct implementation. Then there's the language as implemented. In the language as implemented, factorial A and B in fact never work. Factorial C and D always work, so people's experience writing things like fact C always reinforces their intuition, their intuitive theory of the language, not having read the manual, that fact C is so this is what always works by happenstance of the way we implemented it. This is still a correct implementation because the implementation is allowed to make fact C always work. And then there's finally the most important one, which is the language as understood by its users. So nobody wrote fact A and fact B. I think one person did write fact D. I don't remember. It's in the paper. But in any case, fact C is the one that everybody wrote expecting it to work. So this was the language as they understood it. They understood fact C to be a correct program. So you lay these three on top of each other, you get this very interesting Venn diagram.
I love it.
Yeah, so let me just be quiet while you guys all scan your eyes over the Venn diagram and understand all the different regions. Okay, so the sweet spot is where all of these things align. The vacuum is also alignment. Those are the things that must not work, that never work, and that nobody expects to work or nobody tries to write. Everything else besides those two sweet spots, everything else is anomalous. But most programming is programming in a world in which these things are not perfectly aligned. Fact C is the uncanny zone, which is the language was good enough in terms of what it was providing that people formed an expectation that was ahead of the language as we designed it. And that discrepancy, that they wrote programs that were actually incorrect but happened to work, is the uncanny zone. So when you're faced with a discrepancy like that, when we were faced with a discrepancy like that, our thought was, okay, how can we fix the language so that fact C becomes correct? How do we learn from the misunderstandings of our users to say maybe our users were cleverer than we were in forming a theory of what the language should be doing, and how can we meet those expectations? So one thing is we could just declare what the implementation does to be the semantics, and that would include fact C. But the problem is that if you expect programs like fact C to work, you expect a program like multi-A to work, which it doesn't really matter. I'm going to skip over the actual multi-A, but the key thing is that the theory that you had that led you, that was reinforced by the fact that fact C worked, that the intuitive theory that you create would lead you to write programs like multi-A, which would not actually work. But until you actually write it, when you write it, you're surprised that it doesn't actually work because it's inside your expected to work category. So this is multi-A, and then here's how we fix it with this multi-mutually recursive thing. which implements some static approximation of fairness. It doesn't matter. So the adjustment we made to the language design essentially corresponded to growing the language as designed and the language as implemented to include fact C, include multi-A itself, and include most, still not all, unfortunately, programs like multi-A. Ideally, we would have included multi-A in the implementation as well as the design, and fully met the expectations. But the thing to notice is by growing the language this way, the uncanny zone didn't necessarily get smaller. It changed its shape. Now that different programs work, people are going to be programming, getting a different experience from the language in terms of what does work, and they'll form different theories generalizing from their experience, which will be misaligned in different ways. So whether the uncanny zone gets smaller or bigger is not really that predictable ahead of time when you try to meet user expectations, because now the expectations that are formed by yet newer programmers will be different. So what's going on here is each of these boxes wants to be more aligned with the other boxes. There's pressure on each of them towards alignment, but it's a three-body problem. They're all chasing each other, and there's no guarantee that they converge. So in trying to reach that hill, you might go through the uncanny zones, but we're hoping that clever design will get you back out of the uncanny zone into someplace on this weird trade-off between automation and expressiveness, where the expectations that the behavior of the implementation provokes are actually met by the language as designed. And that's it for that talk.